these pictures to be put together in the album. So in our case, it took the picture to arrive to us a lot of time, but what we see is a picture of the object, of the source, when it was very young. And that's what we refer to as the age of the object.
Okay, great, thank you. The next question comes from Mark Kaufman, Washington Post. Go ahead, Mark.
Yes, thank you very much. Just trying to understand something about the presence of the gamma ray burst type supernova and black holes that would be coming from them. Do those also exist and they occur in the Milky Way, or is this something that is, was further back in time and as a result would be very different in that sense?
This is Avi. Gamma ray bursts occur in all galaxies. They just occur much less frequently than supernova. Only a small fraction of all collapses of massive stars end up in a gamma ray burst. So in a galaxy like our own, we have to wait a long time before we will see one gamma ray burst. We only have to wait a century or so before we see a new supernova. And so it's only a question of how long you need to wait. Now, there are many more galaxies filling up the universe so that you don't have to wait that long if you were to observe the entire universe. So we are seeing a gamma ray burst every day simply because we are looking at many, many galaxies at once. The conditions necessary to make a gamma ray burst are very special. Not only that you need to make a black hole, the black hole needs to produce jets of material moving close to the speed of light. And the jets should be able to penetrate through the envelope of the star and reach the outside world before they slow down. So it's quite possible that some gamma ray bursts do not make it. Some fail and end up in a supernova explosion. We don't know in this particular case of a supernova whether that was the case, or perhaps a neutron star formed and then material fell onto the neutron star to make a black hole. It's, of course, possible that the black hole formed just at once at the beginning and then helped to power this very energetic supernova. This is one of the brightest supernova that we have seen.
Great, thank you. Our next question comes from Irene Klotz at the Discovery Channel. Go ahead, Irene.
Thank you very much. I was just wondering of which of these two theories you all think is most likely. You laid out a really nice presentation for what it would mean if it was a really young black hole, but it seems that that whole kind of line of reasoning might not even be right. So if you maybe can just put some context or some way of understanding which of these two theories you think is more likely. Thanks.
Well, I don't think that we can definitively answer that just yet. We have, several years worth of X-ray observations, but the problem is that we don't have a very deep observation to actually look at what the emission from this source looks like in detail. And that's what we need to do in order to test one theory against the other. Right now, we can only look at the X-ray light curve over a long period of time and look at least qualitatively at its X-ray spectrum over that same period of time. And the shape of that spectrum is consistent with both an accreting black hole and also it's consistent with emission from a pulsar wind nebula. If you look at it for a lot longer, you would actually be able to distinguish between the two. So we can't rule out one or the other at this point.
And if I can add, the X-ray luminosity has a special meaning in the case of a black hole. It's the limiting luminosity that a black hole could have if it has a mass of order 5 to 10 solar masses. In the case of a pulsar wind nebula, you could have a variety of X-ray luminosities since the emission there is not powered by accretion. And so if indeed it's a black hole, the understanding of why we're seeing this particular luminosity is more straightforward.
Oh, and I'll add too, this is Kim, there are other supernova remnants that are being looked at to see if they can see evidence for accretion showing up. And so far, that's not been the case. So we're seeing something here that we've not seen in other objects, which leads me to favor, just personally, the black hole interpretation.
Let me just take a quick moment to remind folks that if you're participating online, you can find out more information about Chandra and this discovery at www.nasa.gov/Chandra and at chandra.harvard.edu. Let me take any questions in the audience if there's anything further. Okay, any questions by phone? Okay, then with that, we'll end today's media conference. I'd like to thank the panelists for their time today. Again, thanks to everyone for joining us, and have a great day.